We already know how to find the antiderivative of a very specific product of f of g of x times g prime x using the U substitution. The question is, are there more products for which we can find the antiderivatives? And the answer is yes. Integration by parts, for example, is a way to evaluate integrals of product of two functions, in a condition that it is possible to differentiate one of them and it is possible to find the antiderivative of the other. So if you have a product, you want to be able to differentiate one of those functions and integrate this. When I say integrate gx dx, I mean also if gx is 1, that you will be able to integrate dx, which is always possible, because the integral of dx is just x. Integration by parts is the antiderivative of the product rule, exactly as the U substitution is the antiderivative of the chain rule, and I'm going to show you that. So let's start showing this by first of all writing the product rule for derivatives. I'm going to write it slightly different than usual, as you can see. Now we're going to take antiderivative of both sides. Now I'm going to use the fact that the antiderivative of the derivative is the function itself. And I get that. Now I'm just writing this in a different order, okay? So as you can see, I'm just subtracting for both sides the integral of gx f prime x dx. And here you will understand what I was talking about. This one must be differentiated. Why? Because on the other side, I have f prime x. And what about this one? On the other side of the equation, I have this one, which means that this must be integrated. So we are getting that this is actually integration by part. But the usual notation is not exactly this one. So let's change a little bit the notation here. G prime x dx is a differential of the function g. It is customary, okay, to substitute v for g of x, and that's why g prime x dx is dv. F prime x dx is the differential of x. And it is customary to denote fx as u. So f prime x dx is the differential of u du. So now integration by part can be written differently. This is the classical way of integration by part. The integral of u dv equals uv minus the integral of v du. We can easily remember this by noticing that here we have u and we have dv, so definitely the u is the one we have to differentiate, and dv is the one that is needed to be integrated. So we already differentiated u and we have du. We already integrated dv and we have v. So first of all, we are writing u times v. And then we subtract the integral of v du. If you noticed, I will always preserve this order in integration by parts. On the right side, I write u and dv. And then uv is kind of the diagonal. And here I know that I have still to integrate v and du. Example. We will try to evaluate the integral of x times sine x dx. Both function x and sine x can be easily integrated or differentiated. So let's on purpose choose u to be sine x and dv to be x dx. So the integral of x times sine x dx is now going to be written, because I want to write it as u dv, is going to be written as integral of sine x times x dx. So now let's do the process, at least start to do the process. So u equals sine x, it needed to be differentiated. And I get that du is cosine x dx. dv equals x dx. This is needed to be integrated. And I get that v is x to the power of 2 over 2. And I get that. We got an integral which is more complicated than the original one if you look. It's because we didn't choose the right u and v. It is not a mathematical error to do that, just not useful. So you have to remember that the goal of any integration technique is to make life easier. So if we get an integral that is much worse than what we started, it means that we are not using the right technique or that we didn't apply the technique right. So in this case, we are getting an integral of x to the power of 2 cosine x dx. This integral is much worse than the original of integral of x sine x dx. So we are going to change our minds and we are going to take u differently and dv. So now we are going to redo it nicely. We observe and we see that one function is differentiated and the other one is integrated. So the whole idea is that if you have x is to reduce the x, because when I differentiate x, I'm going to get 1. It's going to disappear. On the other hand, sine x, I call it a loopy function, because if I will integrate or differentiate that, I'm going to get plus or minus cosine x. And then I can do it forever, but it's going to be from plus minus sine to plus minus cosine and so forth forever. So the right really choice here is going to be this guy is going to be the u and sine x dx, the dv. So now we are going to do the process and now it's going to work nicely. U equals x and we need to differentiate, or if you want to find the differential. So du equals dx. dv equals sine x dx. And when we integrate that, we get negative cosine x. So now, diagonal minus the integral of everything that is on the right side. So it's negative cosine x dx. Let's simplify a little bit the algebra here. And even we can do it because we get plus integral of cosine x dx, which is just sine of x. So we end up with an answer, and as you can see, we started with an integral which is complicated. The integrand was x sine x, and after we used this technique, we were ending up with a really very easy integral. It means that what was done here was in the right way, and that's the way to do that. So in this case, we have reduction and loopy. So if you have reduction and loopy, you want to use this technique to get some reduction. And this reduction will occur if you will differentiate this one. So this guy has to be the u. Sometimes we have no choice. If a function does not have a non-antiderivative, it must be differentiated. So in this case, it has to be the u. Examples are ln of x and all inverse trigonometric functions. So let's take example with ln of x. So the idea here is that the u has to be ln of x just because I don't know how to integrate ln of x. If I would have known how to do it, I wouldn't need integration by parts. So the u is this, and we are getting that du equals dx over x. We don't have other choice but to take dv to be dx. Okay, that's easy. It means that v equals x. Now let's put everything together. First, the diagonal minus the integral of those two. Do small algebra, cancel the x, and you get x ln of x minus the integral of dx, and the integral of dx is just x, it's really easy. So you get x ln of x minus x plus c. Well, we usually write like this. And we are done with integration. By the way, as usual, you can differentiate the answer and see that everything that we did was right.